Weisenfeld Technical Microcourse provides a concise introduction to antenna technology and RF fundamentals. The course explains how antennas, frequency, signal strength, and radiation patterns impact wireless network performance. It is designed to give practical insight for designing, selecting, and deploying antennas in real-world RF systems. An antenna is a device that transmits and receives electromagnetic waves, enabling wireless communication between devices. It works by converting electrical signals into radio waves and vice versa. Antennas are used in a wide range of applications, including TV and radio broadcasting, as well as radar systems, where they transmit signals and analyze reflected waves to detect objects, measure distance, or determine speed. In modern technologies such as Wi-Fi, 4G, and 5G networks, antennas play a critical role, particularly at base stations. Mobile phones also contain built-in antennas, allowing them to communicate with cellular networks and Wi-Fi access points. In summary, antennas are fundamental to all wireless systems, enabling the transmission and reception of signals that make modern communication possible. Introduction to antenna technology. Antennas are available in a wide range of specifications, where characteristics such as dBi, beamwidth, and efficiency directly impact coverage, interference, and overall performance. Efficient antenna design and correct antenna selection are essential. Poor antenna choice or installation can lead to increased interference, reduced coverage, and degraded signal quality, ultimately impacting throughput and reliability. As passive devices, their effectiveness depends heavily on correct integration into the overall network design. Therefore, understanding antenna behavior and selecting the appropriate type for a given use case is critical for achieving optimal RF performance. Radio signals are represented by time-varying voltage and current, with antennas typically connected via coaxial cables to an RF interface in Wi-Fi APs, IoT devices, or repeaters. An antenna's physical dimensions, impedance, filtering, and geometry are engineered to support single-band or multi-band operation across the required frequency bands, maximizing radiation efficiency and power transfer. Antennas are generally passive, non-powered components. Antenna design is application-dependent and used in systems such as cellular systems, 4G LTE, 5G NR, Wi-Fi and IoT solutions, and/or radar systems. Frequency describes how fast a signal or wave repeats per second. Frequency is measured in hertz. It can be described as this: 1 hertz equals 1 cycle per second. 1 megahertz equals 1 million cycles per second. And 1 gigahertz equals 1 billion cycles per second. In RF systems, the frequency affects different aspects such as range, antenna size, and penetration through obstacles. A useful rule of thumb is the trade-off between penetration and range. In general, lower frequencies provide longer range and better penetration, which often allows them to support more users. Higher frequencies, on the other hand, typically offer higher capacity due to wider bandwidth, but they have poorer penetration and therefore usually support fewer users. The frequency spectrum can be thought of as a shared space for wireless communication. It is a limited range of frequencies that must be carefully divided between different users, such as mobile network operators. The spectrum spans from very low frequencies to extremely high frequencies, and each part behaves differently when it comes to range, capacity, and penetration. To make efficient use of this shared resource, the spectrum is divided into frequency bands, each intended for specific applications. In mobile communication systems like 4G LTE and 5G NR, commonly used frequency bands include 690 to 960 MHz, 1710 to 1880 MHz, and 3.5 to 3.8 GHz. Because the frequency spectrum is limited and shared worldwide, it is regulated internationally by the ITU, and nationally by authorities such as the FCC and CEPT. Licenses are issued to ensure that different actors can operate reliably without causing interference to one another. Amplitude describes how strong a radio signal is. It is defined by the size of the electromagnetic wave's oscillation relative to a zero reference level. When the amplitude is high, the signal power is high, and the signal is strong. When the amplitude is low, the signal power is low, and the signal is weak. In practice, amplitude is expressed as signal strength, usually measured in dBm. Signal strength directly affects how far a signal can travel, how good the signal quality is, and how easily the signal can be detected by a receiver. The relationship between amplitude and noise is also critical. A higher amplitude means the signal rises further above the noise floor, providing better resistance to noise. A lower amplitude means the signal is closer to the noise floor, resulting in poorer resistance to noise. Let's start with dB, or decibel. dB is a logarithmic scale used to compare power levels. A change of plus or minus 3 dB means that the power has either doubled or been reduced by half. Next is dBi. dBi describes antenna gain, meaning how effectively an antenna focuses or receives radio energy in a particular direction. It does not mean that the antenna creates more power. Instead, it shows how the existing power is redistributed in space. EIRP stands for equivalent isotropically radiated power. EIRP describes how much power a radio system effectively radiates in the direction where the antenna gain is highest, compared to an ideal isotropic antenna. Here is a simple example. Imagine a transmitter that outputs 20 dBm of power. The antenna has a gain of 6 dBi. The cable and connector losses are 1 dB. To calculate EIRP, you add the antenna gain to the transmit power and subtract the losses. 20 dBm plus 6 dBi minus 1 dB results in an EIRP of 25 dBm. This means the system radiates the same power in its strongest direction as an ideal isotropic antenna would if it were transmitting 25 dBm. Imagine an isotropic antenna as a perfect, glowing ball of light. The light spreads evenly in all directions, upward, downward, and sideways. Every direction gets the same amount of energy. This perfect, theoretical antenna is defined as 0 dBi. Now imagine gently cutting that glowing ball in half. Instead of spreading the light everywhere, you push all the energy into just one half of the ball. Nothing new is added, the same energy is simply focused into a smaller space. Because the energy is more concentrated, it travels farther in that direction. This is what we call about 3 dBi of gain. If you cut the half ball in half again, and focus the energy even more, the beam becomes narrower and reaches even farther. This gives you 6 dBi, and the process continues the same way for higher gain antennas. So why does dBi matter? A higher dBi means longer range, but with a narrower beam and less coverage to the sides and behind the antenna. A lower dBi means shorter range, but a much wider and more even coverage area. In simple terms, dBi describes how focused the antenna's energy is, not how much power it creates. An antenna pattern describes how an antenna radiates or receives energy in different directions. It shows where the signal is strongest, main lobe, and where it is weaker, side lobes. Common types of antennas include omnidirectional antennas, which provide coverage in all directions, and directional antennas, which focus energy on a specific direction. Antennas can be mounted on poles, ceilings, or walls depending on the application. The choice of antenna depends on coverage and design requirements. Omnidirectional antennas are suitable for uniform coverage, while directional antennas are used to focus the signal, increase range, or reduce interference. Factors such as gain and the installation environment should be considered to achieve optimal performance. Antenna polarization describes the orientation of the electric field of a radio wave as it propagates through space. The most common types are linear polarization, where the field oscillates in a single plane and vertical or horizontal, and circular polarization, where the field rotates as it travels. In modern wireless systems, cross-polarization, also called X-polarization, is widely used, typically combining in the range plus 45 degrees and minus 45 degrees polarized elements within the same antenna. In MIMO systems, multiple antenna elements with different polarizations are used to transmit and receive parallel data streams. In massive MIMO systems, these dual polarized elements are combined with advanced beamforming. Polarization is created through the physical design and orientation of antenna elements, and it is leveraged together with beamforming to maximize performance and spectral efficiency. VSWR, or voltage standing wave ratio, describes how well the antenna is matched to the transmitter. In simple terms, it tells us how much of the transmitted power is sent out into the air, and how much is reflected back toward the transmitter. Imagine sending power down a cable toward an antenna. If the antenna is well matched, most of that power flows smoothly out and is radiated as a radio signal. Only a very small amount is reflected back. This is called low VSWR. With low VSWR, the system works efficiently. You get good range, good performance, and safe operating conditions for the RF equipment. Now imagine the antenna is poorly matched. When the power reaches the antenna, a noticeable part of it cannot leave properly and is instead reflected back toward the transmitter. This is called high VSWR. High VSWR means less power is actually radiated. As a result, range and performance are reduced, and the reflected power can cause heating and stress that may damage the transmitter over time. Return loss, measured in dB, describes the same effect as VSWR, but on a logarithmic scale. A lower VSWR always corresponds to a higher, better return loss. Typical reference values help put this into perspective. A VSWR of 1.5 to 1 corresponds to a return loss of about 14 dB, meaning only around 4% of the power is reflected. This is considered a good antenna match. A VSWR of 2.0 to 1 corresponds to a return loss of about 9.5 dB, meaning roughly 11% of the power is reflected. This is considered a poor match and should be avoided if possible. In short, low VSWR means more power goes out through the antenna, and less comes back to cause problems. When designing an RF network for indoor environments, especially in buildings with fire compartments, it is important to start with the building itself. The structure, layout, and materials of the building have a major impact on how radio signals behave. Radio signals do not travel freely indoors. As they pass through walls, floors, and ceilings, they can be weakened, blocked, or reflected. Different materials interact with radio signals in very different ways. Frequency plays a key role in this behavior. For example, Wi-Fi at 2.4 GHz generally provides longer range and better penetration through walls. Wi-Fi at 5 GHz, on the other hand, offers higher data capacity but is more sensitive to attenuation and therefore requires antennas to be placed closer together. The same principles apply to 5G networks, which operate across a wide range of frequencies. Lower frequency bands provide broader coverage and better indoor penetration, while higher frequency bands deliver higher capacity but are more easily blocked by walls and obstacles. Building materials are equally important. Materials such as gypsum and drywall allow radio signals to pass through relatively easily. In contrast, reinforced concrete, metal structures, and steel walls can significantly attenuate or even block RF signals entirely. Because of this, RF and antenna design must always be adapted to the building. This includes selecting the right frequency band, choosing the appropriate antenna type and radiation pattern, deciding on antenna placement, and setting the correct transmit power. By considering the building, the materials, and the operating frequency together, it becomes possible to design an RF network that delivers reliable coverage, good performance, and predictable results. In this course, we have explored the fundamentals of RF network design and antenna technology. We started by understanding how radio signals behave, how energy is distributed in space, and how overall system efficiency is achieved. We learned that antennas are passive devices that both radiate and receive radio frequency energy, and that the choice of frequency has a major impact on range, penetration, antenna size, and system capacity. We also discussed that the radio spectrum is a limited and regulated resource, and that every RF design must comply with specific frequency bands and power regulations. Antenna gain, expressed in dBi, was explained as a way to focus energy. Higher gain provides longer range with narrower coverage, while lower gain offers shorter range with wider and more even coverage. We then connected this to EIRP, which defines the effective radiated power of a system and plays a key role in both coverage planning and regulatory compliance. Finally, we looked at the importance of impedance matching. Low VSWR and high return loss ensure that power is radiated efficiently and that RF equipment is protected from reflected energy. We also saw how signal strength in relation to noise determines link quality and coverage. Thank you for taking part in this course. We hope it has given you a quick and clear overview of antenna technology and the key principles behind RF network design. Before you go, don't miss what's coming next. At Wiesenfeld Tech, we are building a growing library of high-quality technical microcourses, delivered through modern e-learning. The courses are free, short, practical, and designed to create real value. On our YouTube channel, we will continue to explore many smaller technical topics. Areas that both beginners and experienced technicians often find interesting and useful from a technical perspective. By subscribing, you'll get access to new content as soon as it's released and be the first to discover upcoming microcourses. Subscribe to our YouTube channel today and explore more at www.wiesenfeldtech.com. We look forward to continuing the learning journey with you.